Hi everyone, welcome to our next lesson. Remember we had 7-4 in the last class, and today we will start a new unit that's logarithmic functions. If you looked at the book, we are skipping the 7-5. That's the last lesson of exponential functions. The reason why we are skipping it because it requires a lot of calculators, and I am not sure how many of you have the CX calculator downloaded to your computer. If you haven't done so, you can still download it. Remember the instructions I put on the Google Classroom a couple of weeks ago. Just follow it, download the correct version to your laptop, and you can still work on it. But now we will just skip it. We will start the new unit. We will try to cover the most important lessons of these remaining units. So basically we are done with exponential functions mostly, and today we will start the unit 8. So we will do 8-1, so please find the page 399. Logarithmic functions. So what are logarithmic functions? Let's summarize them very shortly. You know the exponential functions, right? How they come from all the way to negative infinity and increases unboundedly, right? All those like exponential growth, geometric growths are represented by exponential functions. So logarithmic functions are just inverses of them. You know how the inverse functions are? It's just that. So logarithmic functions are just the inverse of the exponential function. So what you know about exponential functions, we'll mostly talk about the same but the opposite way. Like domain and range will be switched. Like horizontal asymptote will be replaced with vertical asymptote. Y-intercept will be replaced with x-intercept. All this kind of stuff. So logarithmic functions are so. So why do we learn about logarithmic functions? In a nutshell, logarithmic functions are everywhere actually. So in just one sentence, logarithmic functions are related to very big numbers and very small numbers. Like what? You know the distance from here, the world, to the like any other planet. It's like kilometers, right? Big numbers. In order to calculate them, we may prefer to use the logarithmic function since the distance is very high, right? So we can use the logarithmic functions on this one. Or very small numbers, like maybe even much less than 1 inch, much less than 1 millimeter, right? 0.000001 centimeter, something like that. We may want to use logarithmic in this one too. We use logarithmic in chemistry too. Maybe you learned or not. The half-life of the elements is kind of like this thing is used with logarithm and exponential functions. All very big changes. You have a lot of money and you're making a lot of profit, right? And you're trying to calculate how much you will have more and more in the next 20 years. That might be represented with logarithmic functions. So basically, anything very big or very small can be represented with logarithmic functions. That's the idea. So let's go in deep. So as you can see, this is on page 399. We have a table. I just copied it here. You know, we have the y is equal to 2 to the power of x is an exponential function here. We plug some numbers, -3 all the way to 3, and we got numbers 1/8 to 8, right? You know how to do these. You just plug them and you get these answers. If we revert this and if you try to find the inverse function, as you can see here, that will be x is equal to 2 to the power y. Remember how we do the inverse function, we switch x with y. That's what happened here. And if we try to calculate those numbers again for these, when we plug 1/8 into x, looks like y will be -3. When we plug 1/4, we got -2, so on, so on. And remember the graphs. When we graph the exponential function of 2 to the power x, remember how it comes along the x-axis and increases unboundedly. This time, if you combine the numbers for x is equal to 2 to the power y, you see the green function, it will be very similar to the blue one. It's this time coming along the y-axis and increasing unboundedly again. So we have the blue function, the original exponential function. The green one is the inverse, still represented by exponential, but we will convert this to the log later. So basically, as you can see, these are inverse functions of each other. Remember the line. This line is called y is equal to x. This line is our symmetry line, the mirror. So remember, if this curve is symmetric over the line with the green one, We can say they are inverse of each other. So look at the numbers reverted. We have 0, 1 here, but we have 1, 0 here. We have a 2, 4, a point on the exponential function, but we have a 4, 2. Looks like everything is switched. So what you know about exponential functions, about domain range, they are reverted too. You know how we have the x-axis is the horizontal asymptote? This time for the green one, we don't have that. We have the y as the asymptote. We call it vertical asymptote. Or you see the y-intercept for exponential function. Now it's not there anymore. Instead, we have x-intercept. Alright, so this is the idea of the logarithmic functions. Just inverse of the exponential functions. Okay. Let's see how we can represent the log function. So this is on page 400. Oh, it's no, still page 399. I would like to look at this symbol here. Let's see what it says. Suppose b is more than 0 and other than 1, x is also greater than 0. We represent a logarithmic function as this: log base b of x is equal to y. This is how you read it. Log, we say log base b is the base number, x is the standard number, is equal to y. Can be represented as b to the power y is equal to x, which means, yes, we said that this is logarithmic. This can be represented in exponential, or vice versa. It can be represented back with the logarithmic function. That's the case. Okay? Any exponential equation can be represented in log equation, or any log equation can be represented in exponential equation. For example, this example here, I would like to look at this one first. 2 to the power y is equal to 8, right? 2 is the base, y is the exponent, they are equal to 8. If you want to write in the log form, it is just like that. 2 is the base still, the 2 is the still base. It doesn't change, it stays same. Extra, you just put log at the beginning because you're converting to exponential equation to a logarithmic equation. So that will be a log 2. Here is the case. Do you see y was with 2 and 8 is on the other side? This time y and 8 switch, and 8 goes with 2 and y goes to the other side. That's the idea. One more time. 2 becomes the base. If you're converting an exponential equation to a logarithmic equation, 2 is still same. It is the base. You say log base 2. Make sure when you write the 2, it's a little bit lower and closer to log. That should be separated, distinguished from the number 8. And y and 8 here they switch. 8 goes inside while y goes outside. If you can do that, you can convert an exponential equation given to a logarithmic equation. Or the other way around. Let's say you are given the logarithmic equation and you want to have it in exponential form. This time you erase the log, 2 stays same, 8 and y, right? They switch. That's it. Base 2 will stay same, 8 and y, whatever inside and outside, they switch. Inside becomes outside, outside becomes inside number. That's the case, okay? So let's see how we can write an exponential or write a logarithmic equation and exponential equation. Example 1. So we are given that log base 4 of 64 is equal to 3. So if we want to write this one in exponential, you see how we have log and we have 4. 4 is the base, 4 stays same. But do you see 64 and 3? They will just switch. 3 will become the exponent and 64 will be the standard number on the other side. That's it. That's how we can write a log in exponential. Same over here. Right? Log 3 is the base number. You will be hearing me saying the base this time is 3, just like how the 4 was base here. And 3 will now go with -5, but -5 will be our exponent. Is equal to 1 over 243. You can have any kind of number on the right side. A fraction, a decimal, even negative, that's fine. Okay, that's the case too. Let's look at the next example. We have 9, here is the base, right? Always start with the base number, 9. 1 over 2 was on the other side. Now inside with 9 but exponent equal to a 3. That's it. These are the exponential equations equal to logarithmic equations. That's definitely fine doing the backwards too. Alright. let's see those examples now. This time we are given exponential, as you can see, and we are looking for logarithmic. How? 7 is the base, right? Okay, so since we want the log, then write the log, L-O-G. 7 is the base. Make sure it is like a little bit smaller or just like lower, or at the same, not at the same level log. Just put it a little bit lower here to distinguish from the other numbers. You see 6 and 117, 649, this big number here, they will just switch, and the number here 117, 649 will be inside and 6 will be on the other side. That's it. Same here, write the log. 8 is the base. The base never changes, it is fixed all the time, but the other two numbers, -3 and 1/512, they will just switch. We will have a 1/512 here, and the -3 is outside. Doesn't matter, you can have fractions, negatives, any kind of numbers most of the time. It's not the point. The point is writing the numbers in the correct spot. Let's look at this one. 8 to the power 2 over 3 is equal to 4. Obviously this is an exponential equation again, so we will have a log here if you want a log equation. 8 is the base, 8 is here again, 4 is inside, 2 over 3 is outside, like that. That's it. Log base 8 of 4 is equal to 2 over 3. Log base 8 of 4 is equal to 2 over 3. That's what it is. Alright, so these are examples on 399 and 400. Please do the check question. Maybe you can pause the video and just do the check question. I will give the answers of the check question at the end of the video. Alright, so this is the first objective. What is the logarithmic functions and how do you rewrite exponentials and logs back to each other? And the next one. Let's see how we can calculate logarithmic equations, expressions. We can definitely use calculator, but not right now. Later on when we have complex things, we will definitely do that. So one more time, make sure you have a complex calculator, like I mentioned, CX calculator. So download it. That's in the Google Classroom. Code is over there. You can use it for 1 month. I think that will be fine. That will just cover us for the entire year. So just download that. That will help you if you haven't done so. So let's see how we can calculate this. Log base 21606. As you can see, 216 is the base, and we are looking for what is this equal to? Question mark, right? Since we have limited information, knowledge about the logarithmics, we definitely should convert this back to exponential equations as this one. You know how 216 is the base, and the question mark and 6, they will switch, and question mark is here, like that. It's just equal to 6, right? This is what you have in exponential equation form. Maybe I should say it is 216 to the power x instead of question mark. So when we get the question mark, we got the answer then, okay? 216, right? Remember how we solve exponential equations. The bases must be same. We have a 216 here, we have a 6 here, they must be same. We learned this lesson on 7-2, how to solve a basic exponential equation. They must be equal. If you check on the 216, I feel like it is 6 times 6 times 6, which is 6 to the power 3. So instead of 216, I can write it 6 to the power 3 of x, and just 6 to the power 1, right? If you don't write it, that's 1. So remember the 3 and x multiplies and it becomes a 3x, and 6 to the power 1 here. Once you get the same bases, ignore the 6, right? Ignore the base and just say 3x is equal to 1 and divide both sides by 3. You get 1/3 as the answer. That's the deal. So if there's a logarithmic equation given to you, just do that. Convert it to the exponential equation. Make the bases same. Once you reach the base same, look at the exponents, make them equal and solve it. That's the idea. We will have more explanations and more examples on logarithmic equations later on once we discover more stuff on logarithmic functions. Alright, that's example 3. Let's look at example 4. This time there is a word problem. It says the air pressure outside of an aircraft can be determined by the equation P is equal to B times 10 to the power negative 9H over 100, where B is the air pressure at sea level. Looks like B represents the air pressure at the sea level, and H is the height, the altitude in miles. If the air pressure at sea level is 14.7 pounds per square inch, write an equation for the inverse function. Looks like they want us to rewrite this equation, but inverse. We are looking for the inverse function of this, inverse equation. Let's start with B. Looks like B is given because B was the air pressure at sea level, and it says the air pressure at sea level is 14.7. So it is better to have less letters. So just replace the B with 14.7 because it says so. The air pressure at sea level is 14.7. So there we go. We will have at 10 to the power negative 9H over 100. We are looking for the inverse function, okay? Remember how we do the inverse. We have P and H here. It's like Y and X. It's like Y is equal to 14.7 times 10 to the power negative 9X over 100. Okay, so if you are looking for the inverse, remember how we do that. You switch X with Y, right? The first step. You do the same thing here. You P and H will just switch, and H will be here, and the P will be there. That's the very first step. 10 to the power negative 9P over 100. There you go. Okay. That's the first step. Second step is what? Solve for P. Just like when you switch X and Y, solve for Y. That's the same thing. We are solving for P. It's good to get to the 14.7 first because it's easy. It's just a multiplication. So you divide both sides by 14.7. So we have H over 14.7. This is gone. You just have 10 to the power negative 9P over 100. We divided both sides by 14.7. Okay, maybe I should write here too. 14.7, 14.7. Always get rid of the coefficient first. Now you have H over 14.7, this is together, is equal to 10 to the power negative 9P over 100. If you want to solve for P, it's not that easy. It's not just like elementary operations anymore. You have to convert this exponential equation back to a logarithmic equation. One more time. This is your like Y, this is your B, the base 10, and this is like your X. They will just switch in logarithm. Like what? Remember what I said. If you have exponential, you are converting it to log. Write the log first. And since base is the 10, we have a 10 here. Now the H over 14.7, this thing will together will switch with negative 9P over 100. So you will have here H over 14.7 is just equal to negative 9P over 100. That's it. These two just switch, this one and this one. Alright, so since we are looking for P, we still have to get rid of negative 9 and 100. Basically just multiplying by negative 100 over 9. Remember how we multiply by the reciprocal. Negative 100 over 9 is multiplied on both sides. If you do this way, they cancel. You know, the negative 9 over 100 and negative 100 over 9, they cancel. You just get a P here. That was the point. And we will have negative 100 over 9 times log 10 of H over 14.7. There we go. This is the logarithmic equation. Represents the same situation that is shown here with exponentials, but like we can say this is definitely the same. P is equal to negative 100 over 9 times log 10 of H over 14.7 will be the inverse function. If we are looking for what's the pressure after some certain height, you will just put the h here, number, and see what's the pressure at that altitude. That's it. Okay. Alright, so this is the end of example 4. Let's see the next objective. Now we are going a little bit more advanced, and we are seeing what the logarithmic equations are, logarithmic functions are. So here are the key features, the attributes of the logarithmic functions. So when you graph a logarithmic function, it will most likely look like this one. That means it comes along the y-axis, increasing unboundedly again. It looks like it's going horizontal, but it's not. It just means that it's still increasing, but slowly increasing. The change in the first part is higher than the change in the second part, and so on. That means that the rapidness is going down, we can say that, but still this is increasing. Yes, it's coming along the y-axis from negative infinity and goes all the way to positive infinity on top. If you look at the x-axis, we never cross the x-axis, the y-axis. Here we don't have the left region. As you can see, it's coming along the y-axis and covers everything on x-axis here, and it goes to positive infinity to the right as well. Okay, so mostly logarithmic function will look like this. We represent them with log base b of x, where b is the base here. Again, it can be any number, 2, 3, 4, 5. It will be actually any positive number. That's better to say. You will never see b is a negative number here, or b is 0. Even b is 1. They are not true. You will have this b always greater than 0, right? Represented somewhere here too, but just know that, maybe I should write here, b will be always more than 0, other than 1, and that's it. Something different than x. Do not confuse with the domain. I'm not talking about that. I'm just saying you will never see log base negative 2, or you will see log base 0, log base 1. No, you will see only positive real numbers except 1. Okay. Now let's talk about the domain of this function. As you can see, right, we have the x-axis here, we have the x numbers, but we do not have the negative x numbers, right? So the domain will be starting from 0. It's coming along the y-axis. That means you start from 0 for x and go to the right. So the domain for the parent function of any of logarithmic functions, it's gonna be 0 to infinity, like this one. And the range, you see how we said it's coming from negative infinity. You see how this arrow going down and increasing unboundedly again, just like exponential functions, and covers all entire positive y-axis. We can say the range will be all real numbers, a, r, n. So here's the deal. Remember what I said for exponential functions. Domain is, don't worry about domain. We said domain for exponential functions was all real numbers. But this time we say that for logarithmic functions, for the range. The range will be all real numbers, not the domain. So as we said, logarithmic and exponential functions are inverse of each other, right? So the key features will be reverted to. What I said for domain for exponential function now is true for the range for the logarithmic functions. That's the case. Alright? So range will be this time. You don't need to worry about it. Directly say it is all real numbers all the time. Asymptote. Remember how we have the exponential functions as the horizontal asymptote is for them. Here we have the vertical asymptote this time. It says asymptote, but I would like to specify it with vertical. Why do we say vertical asymptote here? Because if you look at these two functions, doesn't matter which way, you will see the y-axis here on both is the limit that the function never crosses. We can just experiment this on a calculator and see when we get zoom in here on the y-axis, you will see the function never crosses the y-axis. So that means we have an asymptote here, but this time it is vertically. We had it horizontally for exponential functions. Now this is also reverted. Yes, we do have asymptote, but this time it's vertical. Okay, so logarithmic functions will always have vertical asymptotes. Exponential functions will always have horizontal asymptotes. That's the deal. Here we have x-intercept is 1, 0 for any parent function. Remember, this was y-intercept for exponential functions. It's reverted now. Symmetry and extrema, don't worry about them, we don't have these. Symmetry, as you can see, there is no symmetry here. At least you should have another curve here, like this one, or even here, like going down or up, so that we can talk about the symmetry. So you will never have any symmetry either on exponential or logarithmic functions, even extrema. So these are not that important. Domain is important. Not all real numbers. It's mostly restricted by a number, but it is x. X is greater or less, some kind of thing. Range is ARN all the time. Asymptote, there will be always a vertical asymptote. X-intercept will be 1, 0 for the parent function, any parent function. But if you have something complex, you need to check that out. It might be something other than 1 and 0. Symmetry and extrema, don't worry about them. Okay, I would like to mention something extra here, how to find the vertical asymptote. How to find the vertical asymptote. Here's how you can see. Doesn't matter. Log base b of x, right? What is the vertical asymptote for this function? You will just look at here. What you have in this box will tell you the vertical asymptote. So since we have just x, you set that x equal to 0, that will be the vertical asymptote. That you see y-axis here can be represented with x is equal to 0. That's the vertical asymptote. Okay, so you will just check what you have in this box and set that equal to 0 to see the vertical asymptote. That way it will help you towards graphing the functions. Okay, that will be it. Or for example, let's say, what if it's not just x, it's something else. Let's say 5 of x minus 4, right? What's the vertical asymptote of this one? Without graphing, how do we know that? Same, just set this equal to 0 and see what is that. That's 4, right? For this function, you see this time it's not the y-axis, it is x is equal to 4, something is shifted 4 units right. That's gonna be our vertical asymptote. So why do I mention that? Next step, we will see how we can graph them. Okay, so while we are graphing these, vertical asymptote will tell us, it's gonna be a good scatterline to start how to graph a given logarithmic function. All right. Let's see one graphing question. Example 5. Remember, we were on page 401. Now this example is on page 402. Example 5. It says graph each function, then find intercepts x, y, domain, range, and behavior and asymptotes if you have any. Okay, so don't worry about graphing. Starting from exponentials, we don't have to graph it like step by step all the time. We have technology, we can use them. We can use decimal VS, we can use any calculator, graphing calculator. But I still want you to find the key features. These key features. Once you find them, use the technology, graph it, and just verify your findings with the graph. That will be just fine. But how we can do graphing, how we can find some certain points, especially towards Alex questions that I will assign 8-1. There might be questions like that, graphing things. I can suggest to find some points towards graphing. If you can look at the book, step 2 on the solution, I just copied that part. 1 over b, -1, 1, 0, and b1. These are 3 special points. There will be these points all the time on the function, where you will see what is b first. Okay, so we just need to find some special points, that's it, and we will verify them on the graph. Okay, so 1 over b, b is the base, right? So I can say b is 6 here, because log base bx, that's how we show any logarithmic function. So b is 6 here. So that means if you look at here, that 1 over b comma -1, that will be a point that is 1 over 6. -1 is a point that log base 6 of x has. That's the first point. Second point will be 1, 0. Remember how I said x-intercept is always there? There we go. 1, 0 will be there for you if it's a parent function. And b1. b is 6, so 6, 1. So we can say These 3 points are 3 special points that belong to the logarithmic function of log base 6 of x. 1 over 6 negative 1, there for sure. 1 0 is there, and 6 1 also. Okay, we will see these 3 in the graphing calculator, okay, and verify they are there or not. So for this one, I will just go to the Desmos. You can use the Desmos too, and see how the graph looks like of log base 6 of x. For this one, you need to see the special functions. Click on that functions. Here you will see, I think it's under the MISC right here. We want the log right. These two are same, but do this one because you have to put the base number. This is a special one, just log, but we use this one, log A. Once you click on that, you will see the log 2 squares, actually 1 6 here and the x here. So there we go. This is our graph. This is how our graph will look like. Remember, it's again coming along the y-axis, increasing unboundedly. It's going right, actually it's slightly increasing at all times. So remember what we say for the domain of this one. We will answer them next. But remember those 3 points we had. We had 6 and 1, right? So I would like to put those 3 points and verify they're actually on the function or not. 6 1 is one point that we have. We labeled it right here. The other point that we had was 1 0 for sure. That should be the x-intercept right here. And here's the last one. That was what? 1 over 6 and negative 1. There you go. Those 3 special points are here. Of course, we can have more points, we can plug more numbers and we get more, but those 3 special points, when you put them here, the curve will for sure come along the y-axis because the vertical asymptote is 0 here. It's coming along the y-axis and increasing and passing through those 3 points that we labeled. So for graphing type questions on the book, actually you can do this way. For sure, find those 3 special points as we do, label them and see them in the technological device and just copy it. That's fine. Okay, so let's go back to our question. We answered the first part, that's the graph, how the graph looks, and the more important part is the key features. Okay, let's do them. X-intercept, y-intercept. Now we are working on the key features: domain, range, and behavior. Before that, we should mention the vertical, asymptote, and end behavior. I will write here end behavior. Okay, remember the graph, we can go back to that. The x-intercept was definitely 1 0, right? If you just say 1, that's fine, but 1, 0 is the better way to say. But y-intercept, what do you say for the y-intercept? Let's go back to it. Right? Y-intercept should be on the y-axis, but when you get close to the y-axis and the function to see if it's crossing it or not, you will see it will never cross it. There will be always just like a little gap between them. Even though they look alike, they are on each other. Actually not. As you can see, I zoomed a lot here and I see there is no intersection. When you go down and more, you will see they're getting closer all the way but never touch each other. So here we will say we don't have any y-intercept. Okay, we may have y-intercept in next cases, but here we do not have any y-intercept because it never crossed the y-axis. So we have to say it is none. Domain. For the domain, again, look at the function. It's coming along the y-axis, so I can tell it starts from 0 and goes all the way to the right. So that means x is greater than 0. But it has to be x is greater than 0, not equal, because it never touched the y-axis. So we are saying that x is greater than 0. Range, remember what I said, don't worry about it. It is all real numbers. As you can see from the graph, it's coming all the way from down, all the way to up. It's coming from bottom to top. So it's all real numbers. Vertical asymptote. Remember what was the special thing that we can say, even without looking at the graph? What you have here in this box must be equal to 0. So x itself is equal to 0. We have nothing to solve here. So that's the vertical asymptote. That means y-axis, the other way to say, y-axis is the vertical asymptote. Because y-axis can be represented by x is equal to 0 is the vertical asymptote. That means we don't have nothing on the left side of this line, x is equal to 0. Okay. Remember how we do the end behaviors. End behavior is like this. When x goes to infinity, that means you go right. Where is this function going to? Or when you go to negative infinity or something else, where is this function going to? Okay, that's the deal. Let's do it. Let's say we are going to positive infinity on the right side. Okay, so we are going to the right, this way, to the right. So when you go to right, the function is increasing slowly, but we can tell this covers the entire positive y-axis. So that means when x goes infinity, this function increasing slowly. So that also goes to infinity. When x goes to infinity, f of x goes to infinity. Or when x goes to negative infinity. Or can we say that? We do not say x is going to negative infinity because we don't have the left side of the y-axis. We can only say x is going to 0 because that's the left end. When x goes to 0, the function is going down and down, you see? So when x goes to 0, get close to 0, the function is going to negative infinity. One more time, we do not say the left hand this time x is going to negative infinity because it's not even part of the domain. Since the domain is starting from 0, we can only say x is going to 0, but the function is going to negative infinity. So that's it. So for graphing, just find those 3 points. What is more important is to find those attributes, the x, y intercepts, domain, range, vertical asymptote, and behavior. So make sure when you're graphing stuff, make sure you include these key features. We have 1, 2, 3, 4, 5, 6 key features. Okay, that's how you will do. Let's do one more. That's part B, 6B, that's 5B, that's on page 403. We are just doing the same way. These points will there be all the time, and B this time is not a 4, it's just 1 over 4, that's okay. So here are the points that we will have. 1 over 1 over 4, I'm talking about this, because it's 1 over B, right? So then it's 1 over 1 over 4, negative 1. There will be a point like that. Second point is 1 comma 0 for sure, and the other one is just, maybe I should have write it next to it because I will need space. Okay, the next point will be just 1 0, and the last one will be just b1, that is 1 over 4 itself and 1, right? These are the points. If you just fix this point, you know how we don't write it, it's just going to be 4 negative 1 is the first point, 1 0 is the second one, 1 over 4 1 is the last one. Let's just graph the log base 1 over 4x and see those 4 points over there. Okay. Okay, same thing, go to the functions, click on this and get the log a or log b, mostly we say that. That's 1 over 4, right? Not like that, of course. Should be 1 over 4, but I don't know why it doesn't let me. I'll just put 0.25, guys, okay, because that's 1 over 4, but still didn't work here. Let's see this one more time. 0.25, that's 1/4. I just prefer to write it that way since it didn't understand. So there we go. This is our log base 1/4 of x. Okay, this is gonna be our function. So let's see those points that we get. We said that we have a 4 and -1, right? That's one of the points. There we go. That's here. Let's label it. Second one for sure 1, 0. Again. And the other point we got was 1/4, 1, right? There we go. We got all these points here together. Okay, this time, as you can see, this is reverted, right? It's still coming along the y-axis, but decreasing here. When you go right on x, when you increase your x numbers, the function value is always decreasing. That's okay. This is like exponential growth and decay. This is a decay graph because it's decreasing. Okay, you can relate this to that. You know, the base was 1/4, 0.25. You can say that if that number is between 0 and 1, it's gonna be a decay. If that number is more than 1, just like the previous question with it, like 6, that will be an increasing, that will be a growth function. So we can say the same thing here. This is the graph. This is how the graph will look like. Okay, before we go to key features, let's just see what they are. The function is coming along the y-axis, right? We do not have a y-axis, y-intercept again, because it never crossed the y-axis. We do have an x-intercept. We have a vertical asymptote again one more time, that is the y-axis itself. This is the border, the function never crosses. The end behavior when x goes to infinity, when x is increasing like 2, 4, 6, 8, 10, 12, 14, the function is decreasing. Or when you approach the 0, when you go to the left, that's still the end 0, the function is increasing. That's the left end behavior. The left end behavior, the function is increasing. On the right end behavior, the function is decreasing. Let's put these all together and let's finish the question. Alright, x-intercept. We have 1 and 0, as you can see from this point too. Y-intercept. We don't have again. Make sure next time you may have it actually after the transformations. Domain, range. Domain is x is greater than 0. Range is all real numbers. Vertical asymptote. Since y-axis is the limit, we have x is equal to 0. Do not just say 0, say x is equal to 0. 0 is a number, x is equal to 0 is a line, a vertical line. We want this. And the end behavior. When x goes to infinity, the right end, tail, you can say the function is decreasing since this is a decay function. Or when x goes to 0, the other end, the left end, this time the function is increasing. You can just tell it from the graph that you have. Okay, that's the deal. Okay. Alright, so we covered a lot of things. Remember, we discussed what are the logarithmic functions, we discussed their key features, we discussed how to convert the exponential to log or log back to exponential. These are the basic things. Alright, let's finish the day with how we can apply the transformations. Okay, so this is page on 402, one page back. I put it here. Let's see what they are. Remember the template for an exponential function. That was something like this for exponential function. b to the power x minus h plus k. Of course, there's an a in the front. A times b to the power x minus h plus k. We learned this one in unit 7. This time the template for logarithmic functions is similar. This time we have log instead, but the others all same. So any transformation, doesn't matter. Next unit we will talk about rational functions. We will have this template again, AHK. Of course, it's going to be modified according to the new type, but still there will be AHK, and the effects of them will be just same. H is going to tell you about the horizontal shift. If H is greater than 0, you go right. If H is less than 0, you go left. Be careful, we have to have a negative sign in the formula here all the time. Remember how it's reverted. When it is +2, that means you go 2 units left. When it's -2, you go 2 units right. Because of the negative sign, we are doing the opposite what it says here. But for the vertical, you're just fine. K is greater than 0, you go up. K is less than 0, you go down. A, reflection and dilation. Okay, reflection, when A is less than 0, you have a reflection over x-axis. But when A is the magnitude, regardless of the negative sign, when the A is greater than 1, it's going to be a stretch. When A is a number between 0 and 1, it's going to be a compression. So dilation means that. Compression and stretch. Okay, dilation means that. Okay, so we are just going fast on this one. You know the effects of AHK is just like same, but it just modified to logarithmic functions. Okay, so whenever it says what are the transformations, we'll just do that. We will see what AHK are and we will tell the effects of them, and we'll see them on the calculator. Example 6 will be our last one. Okay, so let's see what are AHK on this complex function. This time it's not a parent function, which means it is something complex than the basic one. You see how we have 2 here, +3 and -1. We never had this before, but here. Okay, so let's define what's A, H, and K. A is 2, we can tell that, right? H is, since this is supposed to be -3, you remember how the formula was, that must be in x minus h, so you should consider that one x minus -3. So that gets your h is -3, not +3. Or remember, if it's horizontal, you do what it says here, you do the opposite of what it says here. So +3 becomes -3. Okay, but for K, don't worry about it, just copy it as it is. K is -1, that's it. So these are AHK. So let's write the effects of these. 2, right? 2 is something positive. Remember, A has 2 effects, reflection and dilation. We don't have a reflection here. Why? Because A is positive. No reflection at all. But A is 2. It is more than 1. 2 is more than 1. That means it's a vertical stretch. That means just imagine that you're stretching pulling the function from top and bottom. It's gonna be like sharper than the original one. If you compare with log 10, the 2 log 10 will be sharper. So the first transformation is that vertical stretch. The effect of -3. 3 units left, because this is horizontal shift. 3 units left. Left and right horizontal. K is equal to -1. You know that. 1 unit down. We have 3 effects here. We shifted the function 3 units left. We stretched it. Now it is sharper. And we take it 1 unit down. Okay. These are the transformations. Let's see them on the function, on the graph calculator all together. So I will just put them on decimals again, one by one. Okay. And let's see the changes. Remember, I will just graph this one first. The log 10 of x. That's our parent function. We will just start with that. 10 of x, log base 10 of x. This is our parent function. Okay, so there you go. I'll just copy this one. This is the parent function. Now let's graph this one. When we added the 3 plus 3, remember this 3 will make the function shifted 3 units left. Now there we go. We have the new one. It is shifted 3 units left. And now let's multiply it by 2. We will just have the 2 in the front. Guess what happened? If you compare the blue function with the green one, they are originated from the same point, but the green is sharper because it's stretched. It is increasing faster than the blue one. And let's finalize it with the -1, which is the ultimate. we have the function as this: the 2 log base of 10 of x plus 3 minus 1. And you can tell that the function is, when you compare the green one with the purple one, the purple one is shifted 1 unit down, and that will be it. Okay, so this purple one will be our function. It's kind of coming along a line, a vertical line. Here I can tell that's a -3. You see, we have a line between -4 and -2. Let's also put that one to see it better. X is equal to -3 is gonna be our vertical asymptote, and the purple function is coming along that and increasing unboundedly. All right, so for the transformations, just do the same, write all them out here. And for graphing, you can use any calculator, but make sure do it step by step to see the changes. Okay, this will be just fine. For the last page, 404, example 7 and 8, I'm just leaving these to you, so make sure you work on them too. It's just like more comparing two functions, like what's the change of this function based on the given one. It's like basic transformation, so do them as well. And here are the check questions that you should work on while you're filling out the gaps. Remember how you follow on the book. I'll just give you the answers. The check question on page 399. The first question, page 399. The answer should be 5 is equal to 125 to the power 1 over 3. That's the answer for the first check question. Page 401, the check question on top. It should be this. W for part A, W is equal to 93 log base 10 of y plus 65. For part B, when you plug the number 50 into y, you are going to see it is 223 mph will be the answer. Let's turn the page and see if we have another check question. We only have one last. I think it's on page 404 after example 8. So the g of x should be that log base 3 of x plus 4. For the part B, that's just negative log base 3 of x. Alright everybody, so this is the end of the lesson. So make sure you take notes, watch the video carefully, pause it, try to solve it by yourself, see the solution, and if you will have any question, just email me. Okay, so you will have 2 homeworks, one from the book, the odd numbers again, and the other one is just the Alex. I will assign them by Monday morning. Okay, let me know if you will have any questions, and take care.